Hi. Yeah. My name is Cristian. I am from Barcelona. And first thing I wanted to say is that this is my first year doing public speaking. So I'm really sorry for the next 30 minutes. But I felt like I had kind of like a mission here. It's talking about this. Come on, you all know it's true. I mean, I'm sure I'd ask my grandma about Rails. She doesn't know what it is, but she knows it doesn't scale. Go to any Twitter thread. It's a fact. So, despite me never talking in public, I've been going to conferences for 10 years. So I decided to make a little summary, the same as the great speakers do, you know, like a small summary of my whole talk in the first 2 slides. This is my first one. There's the second one. And I really mean it. Because I work at Zendesk. My focus, every day I'm working with making the Rails monolith to scale. And actually, the title of the presentation is a lie. We don't manage 1 billion requests per day. We manage over 2. And I don't think we are doing something incredibly special. For example, don't take it from me. This Twitter thread is from a couple of weeks ago, from Black Friday. Shopify Engineering, they were commenting the incredible amount of data they were managing during those days. And this is my favorite piece of data. 76 billion requests per minute. That's a lot of data. So the thing is that Rails scales, it's a fact, it's happening. It's not something, a theoretical possibility that could happen. No, it's happening right now. So the question is, why is people saying that it doesn't? And I actually have a theory. But for me to explain you my theory, we will need to do some time traveling. By the way, this is Doraemon. He is a 22nd century robotic cat. And believe it or not, he will come back into this presentation, I promise. But that will be later. Now we're going to time travel to 2010. This is me in school. And I was writing my Fair Rails app. I was learning Rails then. And I wanted to add authentication. It's a common feature. And authentication is a hard problem. Believe me. But at the time, I had no idea. So I decided to, do a deep, thorough investigation across the, multiple sources. And of course, I found this fantastic gem called Device. I read the documentation, more like the first paragraph of it, and it just worked. The point here is that authentication is indeed a hard problem. I later became tech lead of authentication at Zendesk, and believe me, it has its quirks. But for 20-year-old me, it didn't feel like that. It felt like, man, this computer science thing is very easy. Okay, for the next part, we need to go back to the time machine and go to 2012. This is a picture of me with the real mats, not the one I have here. I'm very proud of this one. And at that time, I was co-founder of a startup. I was CTO. And like Nate, I was also the only engineer. So the thing is that we were kind of popular. So I had to make this Rails monolith to scale. Scaling is a hard problem also. So I decided, hey, I'm going to use the same method I used before. Going to do a thorough investigation. And thanks God, I found this fantastic gem called ActiveScale. Now you had time to search it in GitHub and read a bit of the documentation of ActiveScale. Again, I read the documentation. My main point on this presentation is to use the parameter scale sufficient but not too much. You don't want to overdo it in the beginning. And that was it. Everything was beautiful and nothing hard. I think we recovered a lot of time for the coffee break, so I think we're fine now. Okay, this was actually bull also. ActiveScale doesn't exist. I made it up, obviously. I think I would bet some of you were searching for it. But my general point here is that scaling is a hard problem. but it's a problem that feels hard. It's not like authentication that we, the Ruby community, we get a free lunch with device. Like I had absolutely no idea about encryption, and I got a state-of-the-art authentication system. My final point, my conclusion is the problem is not that Rails doesn't scale. It's that Rails is so good, it's so easy to use, the learning curve is so smooth, that one of the few problems left for you to solve is scaling. Okay. Now, before going further into the techniques that we use for scaling, I would like to give a few general comments on this presentation. The purpose of this talk is an introduction to the problem of scaling. We're going to give general ideas, illustrated with issues we force scaling to a significant degree. An important point here is that there are no silver bullets that I can offer you. I can just give you a toolbox and you choose the right tool. Because as Tolstoy said, kinda, if every poorly performing system is performing poorly in its own way. Next is the reason why I wanted to talk about this, and I think I'm a bit qualified because I see the amount of data that we manage at Zendesk. Zendesk, we are a customer support company, and we have, the same as in Twitter, the basic data unit will be maybe the tweet. For us, will be the ticket. We have over 16.3 billion tickets, and this again is a lie because this is a number I took in January, so probably now it's more like 19 or 20. Just to give you an idea, this is twice of the population of the Earth. Here you see that graphic design is my passion. So, most importantly, dataset is growing. Around a third of all data was created in the last 365 days, meaning something that is not a problem now is going to be a problem soon. So you need to work for the future. Obviously, this has a real impact on the physical memory that we use. On relational databases, is over 400 terabytes. And we have all other different kinds of storage, but these are only relational databases, mainly Aurora. The tickets table across all shards is 3 terabytes. But this is far from being our biggest table. We have one table, obviously this is sharded, but it's 60 terabytes. This is actually my project this quarter, trying to tame this thing. Finally, before going to talk about the techniques, I want to discuss what I believe is the right mindset for a performance engineer. The point is that I think that performance work is fun. Like I think that a lot of engineers prefer to create new features, like I know new toys. I feel like performance work is fun, and the reason is very, very simple. Is something like this. This is the real result of a real optimization I did at Zendesk, and I think that. Me personally, when I see this, I feel like this. I think if you feel the same as me, you'll be successful as a performance engineer. You'll have the drive, you know. Okay. Now let's have fun and let's discuss the different techniques. First of all, an incredibly basic monitoring. Basically, you don't know. I mean, you cannot fix a problem you don't know you have. And if you're not monitoring, you don't know you have a problem. Moreover, if you're writing a solution and you don't have a way to measure how the solution is working, you are not really doing anything. I mean, you don't know, or being more precise, you don't know what you're doing. So please, monitor. There's different things that you can put monitoring, like metrics, APMs, logs. Said this, at a certain scale, you will find that monitoring can get very expensive. I know, Zendesk accountants always get very scared when Datadog bills arrive at the company. But monitoring is important, and one thing you can do, particularly when you are monitoring performance work, is sampling. I think performance work is it works very well with sampling, because what you want is the signal. You want the signal of the change that you are able to implement. Typically with a sample of 10, 5, even sometimes 1% is good enough for you to know where you are. Next, and also the part of monitoring, is error budgets. And I know what you're thinking. Error budgets are for uptime. You know, is my application up? It's not about latency. But one counter argument I would say is that if your endpoint is working but it takes 10 seconds, it's as good as broken. So please, one thing you can do is just setting error budgets for latency. And we do this at Zendesk. This is a real error budget we have. In the left column, you have the uptime, so the typical error budget. And in the middle and in the right one, you have the amount of the percentage time that the API responded in an acceptable amount of time and in a good amount of time. Obviously, acceptable and good are absolutely arbitrary numbers that we set up. But I still believe it's very useful. You need to set yourself limits. You need to set yourself a North Star to follow, just to understand in which place you are. Next, and this is like part that I think I always disappoint people, is database query performance. Mainly because I think people always expect me to talk much more about that, and this presentation was designed with the idea of talking as little as possible about databases. The title of this talk was originally Beyond N+1. But if you have an N+1, fix it. Said this, I want to comment a few things. Obviously, I will comment the most obvious ones, using database indexes, please. Said this, one thing that we found working with huge amounts of data is that the query optimizer sometimes goes a bit crazy when it has too much data and it starts to have issues detecting the right index. Sharding, obviously, particularly for a lot of companies, you can make very nice shards, meaning dividing the database in multiple databases. This is great if you have typically, a B2B company or something like this, they make for very nice sharding. Next one, this one I like a lot because it's obvious, but I think people doesn't realize how important this is. It's what I call greedy selects. And it comes with ORMs and active record, but it is the default of I fetch everything by default. Select star from wherever, no? I don't think people realize how dangerous this can get with the time. You may be fetching literally gigabytes when you need a few bytes. And this something that happened at Zendesk. We had this nice little endpoint that returned all the objects of a particular table unpaginated. This was by design. And it was only because it was only returning ID and name. So in the end, the response wasn't that big. The payload was small. I think we counted it, and worst case was a few megabytes. Problem. We found a customer that had so basically this table had a lot of columns, a lot of them free text areas. And we had a customer that decided to put, I don't know, super long text there, meaning that to render, I think it was less than 1 megabyte, the customer was fetching from database gigabytes of data. Those gigabytes of data, literally, database was not able to handle them by itself, so it needed to write into memory, to disk, in the middle of a select, which make a crazily slow select. And eventually, database meltdowns, problems like this. This is actually the optimization that I showed before. As simple as using .plug. And finally, about databases, one thing I wanted to comment is that complex database queries have high variability. You may be thinking, hey, I'm checking the mean, the median, and this query seems pretty good. When complex database queries tend to have very bad P99s a lot of times, and P99s are what you want to keep an eye on, mainly for two reasons. One, they're the ones that cause most, again, meltdowns, and second, user experience. Second, user experience. You don't remember, the user doesn't remember, oh, this website is responding in 150 milliseconds instead of 160. Nobody cares. They remember, oh, suddenly I made click and I had to wait 6 seconds. P99s are gold. Next section is caching. And I don't want to discuss caching in general, but I will comment a few things that we do that are a bit different. One is write-through caching. The idea of write-through caching is that you are updating the cache at the same time that you are updating database. And this, said like that, sounds like a very bad idea because literally the idea of having a cache is to have a smaller, hotter storage. However, here in our implementation, this cache is working a bit as the normalized storage. So you have this very complex derivated model that it only appears in the API. It's like the API is returning something that is a mix of multiple tables, and it's a very complicated calculation. You need to pre-calculate it. Every time that there is an update on anything that will be affecting the response of that endpoint, you change the cache or any other storage. It's useful for the normalized objects. This is one example of one implementation of this that we did for a side load on one of our main endpoints. And I think this is a good opportunity to comment on if small changes, if they do matter. This is a 40 milliseconds change, which may not sound like a lot, median, but at the scale, it matters. This endpoint, I think it's tickets index. It's hit 50,000 times per day. I think actually more, but let's say 50,000 times. So this in total is more than 8 full days of computing. That's money. Finally, trade-offs, and this is going to be a lot of fun. Using cache adds complexity. Before you had all your data in one place, now you have duplicated data. Data can become inconsistent. Moreover, caching and key value stores are not trivial and they are not magic. And I think in the Ruby community, we tend to think a little bit as particularly caching and Redis as some kind of magic storage. Actually, I think so often about these issues because I work with cache a lot that it brought me to create what I call the Doraemon paradox. You see, I told you he would come back. By the way, who here knows who is Doraemon? Okay, well, this is so much better than in the US. Okay, so basically, let me explain you who is Doraemon. He's a robotic cat from the 22nd century who has millions of futuristic gadgets in his 4D pocket. Basically, he has a lot of machines that they are basically magic. They can do whatever you want. What particularly fascinated me a lot is the pocket, where everything can fit. Here, he's taking out 4 doors out of the pocket, but he takes boats, he takes whatever. It's like it doesn't make any sense. It's a bit like this. In this way, having a storage where everything fits and there's no order, no logic of what they're putting there, makes me think that maybe the pocket is like the natural evolution of Redis because it's a bit, I think we use it in the same way, no? Yeah. So beyond that, I discovered that Doraemon is an incredible fable about software engineering. Each episode of Doraemon follows the same structure, and I think it's a great fable. Let me tell you. So Doraemon lives with Nobita. Nobita is this 10-year-old kid. He's clumsy. He's kind of a loser, always gets into trouble. And in the beginning of each episode, he has a problem. He goes to Doraemon and asks him, "Hey, Doraemon, could you give me one machine to fix my problems?" And Doraemon eventually complies. And around the middle of the episode, Nobita is triumphant. He's solved the problem. He's winning. But then he starts to misuse the machine. Doraemon typically tells him, "Hey, you cannot do this, you cannot do that." And Nobita does it. And eventually Nobita loses and ends up in a much, much bigger problem than he originally had. My point here is that some technologies particularly technologies that seem very simple, like Redis, like Rails actually, tempt us to misuse them. And I think we should use technology wisely. I think that Rails in specific is a technology that is so simple that it's very easy to think that you master it when you don't really know it. For example, me with Device when I was 22, I had no idea about encryption. I was the master of authentication. No, I wasn't. We should learn about the technologies that we use. Next technology, and this is one I love because I didn't know much about it until a few years ago, is cold storage. The idea for you to understand is like it's an anti-cache. So you have cache is a data storage that is specialized on hot data that is used very, very often. Cold storage is the contrary. You add another storage for data that is rarely accessed. And I think, seeing your looks, I think you are wondering, why would I want to have something like that? I mean, it's obvious that adding more storages is just adding more complexity. And why I would add another storage for data that I rarely need? Well, the reason is that you have too much data. At Zendesk, we have a lot of data, as we were commenting before. And this can be problematic. Database optimizations may not cut it at some point. But there is a solution. What if I told you I can make those tables smaller? Send the amount of data 5 years into the past when the queries were so much faster because you had like, I don't know, 200 terabytes less of data. Why not dividing that storage in multiple ones? Let me explain you how it works at Zendesk. Here I made like a little Zendesk, with a user that has a lot of tickets and a ticket that has many events. And then after some time, you need to decide when data is marked as ready for archival. At Zendesk, and again, this depends a lot on your use case, what we decided is that when a ticket is closed, meaning that the interaction with the user is finished, we wait 4 months, 120 days, and then we mark it as ready for archival. This means that we literally remove it from the relational database and we move it to a specialized archived ticket storage. For archival tickets, ticket archival, historically we use React. We used Dynamo, and I really want to use S3, but I'm not able to convince anyone. Moreover, you will be thinking, hey, this can be a huge mess because I'm breaking a lot of associations. What we do is we create a new skeleton object. At Zendesk, we call it the archive ticket. So all the sessions are still alive. Of course, all the data that makes ticket itself is in the cheaper, nicer storage to be kept. I think I would like to communicate clearly how important this project is at Zendesk. Literally, most of our data is archived. Like this was taken in early this year, so probably over 90% of the data is archived right now. Without cold storage, we wouldn't be having 3 terabytes on tickets table. We will be having 25 terabytes. Obviously, cold storage is a technique that has significant trade-offs. As I was commenting before, now you don't have all your data in one place, you have it in 2 places. You need to this may introduce issues in the product. For example, ordering all tickets may be a challenge if you have them in 2 different places. Making a sort query across 2 databases is impossible, or it's a challenge. You may even think about changing access patterns. You may even say, hey, from now on, the historical data is not accessible from our main APIs. You will have a different access patterns. And I know that this sounds like a change on product, and I think we as engineers, we try to follow the requirements very strictly, but performance is a feature, and sometimes it's the most important feature. So again, trade-offs are worth it sometimes. Finally, and I think this is a lot of fun, designing a product around performance. A few ideas about how to change a product to make it more performant. Product limits. Yeah, I know. Once a platform gets to a certain size, first of all, you need to understand that you have no idea what's happening there. For example, once I wrote a feature that I couldn't roll out because I was throwing exceptions like crazy, and eventually I found that some guy was copy-pasting the whole US Constitution, including all the amendments, into a free text area, making it impossible to parse by, I think it was Ruby. This is one extreme example of someone who was obviously using our system in our wrong way, but sometimes there are completely valid customers that use your product in crazy ways. And yeah, I know that product limits are not sexy. It's not nice saying to your customer, hey, sorry, we are going to limit the API accesses to 1,000 per second. But the thing is that you have product limits already. You have product limits because your product is an application. The applications run on physical machines, on computers. And computers, physical machines, run on the physical world that has limits. So if you don't have a product limit, you still have a product limit. This is the product limit. A database meltdown is the product limit. So please be smart about it and set up your own. Next one is what I call the incredibly enlarging payload. And I think that everybody has been working in the same company for many years, has seen something like that. It's also known as endpoints that return way too much data. Typical story. 5 years ago, you write this new endpoint. It had like just 4 attributes per object. It was really nice and lean and looked very clean. 5 years after, you come back to the same one. It returning 40 attributes. You need a browser extension to parse it because it's impossible to read. It's crazy. This has issues. No, the endpoint is just slower. Complexity has increased. It's very hard to debug. And the payload, the amount of data we send around the internet, that's much bigger. Actually, that's another issue. Like we don't think about the amount of data that we process, but this is a significant element to make something faster. Solutions. Just send less data around. Just limit yourself to the data you need. You can use sideloads. You can use GraphQL. And finally, the last part, what I call breaking down slow workflows. You can do this in reads and writes. No? For the read, one thing you can do is breaking that slow response, slow endpoint into 2. And I know you were thinking that doesn't make any sense. Because if I have an endpoint that takes 3 seconds to respond, and I divide into 2 calls to get exactly the same data, I'm still going to run exactly the same logic, plus double the amount of network time, plus double the amount in the middleware. So it will be just literally slower. Why to do that? Well, because of user experience. If you do something like you make one very fast query, very quick call to an endpoint, and you get some functionality to the user, and then after that, in parallel, you make another query to fill the gaps, for the user experience is incredibly better. For the user, it took 300 milliseconds to load the page, not the 3 point something that took everything. Remember that we write applications for users. User experience is king. And then finally, on the right. This is a bit the same case as in the incredibly enlarging payload. You had this beautiful create endpoint that was just doing one insert in one table. Time passes, there is a lot of associations, audits, whatever. And now suddenly you're doing, I don't know, 10 inserts, 25 updates to create one object. This happens. What to do there? Well, do it partially asynchronous. What you can do instead is when a create call arrives, just create one particular object, and then all the rest do it in a synchronous way. This eventually evolves into distributed systems. Say this, eventual consistency can be painful. It's a different way of thinking about systems. But again, it's worth it because performance is worth it. And my last chapter, special interventions. This is Paul Graham. Do things that don't scale. And this seems like something that doesn't make sense, particularly because we like to think that we are scientists. And it's true. But the reality is that in your SLOs, small customers will have a huge impact. I mean, I'm not going to tell the names of companies, but we knew of specific companies that were very related with incidents. It's the name of the game. So you need to do special things for them. You need to feel a bit like Captain Ahab from Moby Dick, that he's not a normal fisherman hunting, I don't know, 1,000 sardines per day. He spends 1 year, actually his whole life, trying to hunt this big white whale. You need to be like that. Of course, this special intervention thing depends completely on your business. But one thing that we do at Zendesk is splitting accounts. Sometimes when you have a customer that has a lot of activity, it makes sense for them, from a business perspective, to divide into 2. And for us, it's a blessing, because you can distribute resources much better. This is the result of one of them. And finally, I'm concluding here. I would like to leave you with a few thoughts. Main point for me is that performance is about trade-offs. Because there is no such a thing as a perfect system. You are not going to have this nice, cute system that you wrote when the company was starting. Nice, simple, totally normalized database, no duplications, everything is great. What you should get is one system that fits the best the current needs of the business. You need to think that an excessive pursuit of perfection can be counterproductive. You cannot spend all your day trying to get everything. You need to understand priorities. And performance is a priority. However, I think that everybody that is in this room has an advantage. because I think that we at the Ruby community, we know this very well. We accept trade-offs. We are the community that optimizes for developer happiness, which is kind of a crazy or at least a very hippie idea, no? But it's a great idea from a business perspective. Developer productivity is incredibly important. Finally, I would like to leave you with a quote from Matt, and I will read it. I believe that the purpose of life is, at least in part, to be happy. Based on this belief, Ruby is designed to make programming not only easy, but also fun. Well, I hope you had fun.